So now we're going to move on to our level 7 and above work, where we'll use a variety of equations to calculate final velocity, initial velocity, acceleration, and displacement. Okay, so what we can do, we can calculate the final velocity squared as it's equal to the initial velocity squared plus 2 times acceleration times displacement. So what we've got here, as you can see, final velocity is v, initial velocity is u, acceleration is a, and s is our displacement. And if we think about this equation, it will make some sense to us. Okay, so our final velocity is equal to our initial velocity plus our acceleration over a certain distance. So if you think about it, your final velocity will be equal to your initial velocity plus how much you accelerate for and over what distance you accelerate for. Okay, so we can also rearrange this equation into this form here, whereby we can get our distance or our displacement from our acceleration and our final and initial velocities. Best way to get your head around this is if we go into an example. Okay, so imagine we have a horse and it's running with a constant acceleration of 0.45 meters per second squared. It has an initial or beginning velocity of 8 meters per second and runs a distance of 180 meters. What is a horse's final velocity? So using the equation on the previous slide, we have v squared equals u squared plus 2as. Okay. And if you look at the question, it's asking us for the horse's final velocity. So here we go. Final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. Okay. So all we have to do now, or the first step at least, is we need to substitute in those values. Okay, so u we said was 8, so that'll be 8 squared. 2 is a number. Acceleration is 0.45 meters per second squared, and our displacement or distance travelled is 180. So if we go now and type that into our calculator, we should end up with these values here. Notice I put this region in brackets for 2as because often it helps to separate out equations where you've got more than one term. Okay, by term we mean a part with a letter, a variable in it. So we're following BIDMAS, so I'm doing this brackets bit first. Then it would be the indices or the power, that's the I in BIDMAS. So we end up with 162 plus 64. Okay, so if we put that into our calculator, if we add it in our head, we end up with 226 meters per second. Okay, that's our velocity squared. So now we have to find out the velocity. So the velocity, if this is a velocity squared, we're going to have to square root this answer to get our final velocity. And here's where having an idea of the magnitude, the size of numbers really helps, because right now we're thinking our velocity could be 226 meters per second, which for a horse is ridiculous. Okay, so that's 2 times 100 meters and 26 meters per second. So that'd be 2 lots of 100 meters and 26 meters in a second, which no horse can run that quickly. Okay, so now to find v, we square root that. Okay, and we end up with 15 meters per second, which is a lot more reasonable for the speed of a horse, even a racehorse. Okay, so that's a lot more realistic, and that's still really very quick. So when you're cycling, you can sort of get up to 15 meters per second on a flat bit of road quite easily. Okay, So that is our first example. Here's another example. This time we have a car that accelerates at 3 meters per second squared. It has an initial velocity of 0, starting from rest, and travels a distance of 1 kilometer. What is the car's final velocity? So often the tricky bit is working out what equation to use. So we want the final velocity, v. We've got a, we've got the initial velocity, u, and we've got the displacement or distance, s. So once again, we're going to be using our v squared equals u squared plus 2as equation, as shown. Okay, now it's exactly the same process. We're going to substitute on our values, but this time it's a bit easier because our initial velocity is 0. So 0 squared is 0. Okay, plus our 2, which is our constant there, our acceleration, which is 3, and our displacement, which is 1000. Okay, so if we put them into our calculator, do a quick bit of math, we work out that our v squared is 6,000 meters per second. For those of you wondering where the 1,000 came from, okay, if we look, we've got a distance or a displacement of 1 kilometer. And if we remember from earlier, 1 kilometer is 1,000 meters. Okay, 1 kilometer is 1,000 meters. Okay, so what we're going to do now, once again, is we have our v squared. So in order to find v, we need to square root both sides. Square root of v squared gives us v, and now we need to square root of 6,000. This one, we're going to have to type into our calculator. So if you type that into your calculator, then you end up with this answer here. Okay, so the car, when it accelerates over a kilometer, is doing 77.46 rounded to 2 decimal places meters per second. So nearly 100 meters per second. That is really very quick, but understandable when you're talking about a car. Okay, so here's an example of a car that could do such speeds. So this is a Bugatti Veyron. It's the fastest road car around, and I think its top speed is about 300 miles per hour, something in that region. So this value here of velocity is a reasonable value. Okay, so that concludes our lesson. So that was looking at how we can apply more complicated equations of motion, acceleration, velocity, displacement. Thank you very much for listening. Once again, if you have any questions, please feel free to contact me via email, on Google Classrooms, or via SD Connect. Thank you very much.